Hello everyone, welcome to the lecture on Fresnels Biprism. I am M. Satyavani, lecturer in physics, DNR College. In this lecture, I will discuss about the interference fringes formed in Fresnels Biprism experiment and how wavelength of monochromatic light is determined. These are the topics I will discuss in this lecture. In last videos, I have discussed about the phenomenon of interference and the formation of interference fringes. In this topic, the scientist Fresnel used a biprism to show the phenomenon of interference. Therefore, this is called as Fresnel's biprism. Using this biprism, a single wavefront is divided into two wavefronts and the two wavefronts interfere with each other and interference fringes are observed. That is the actual phenomenon in this experiment. Therefore, in biprism, the interference belongs to the type of division of wavefront. This division is done by the Fresnel's biprism. Fresnel's biprism, actually Fresnel's biprism is a combination of two acute angled prisms placed base to base, but it is constructed as a single prism. In biprism, the acute angle is less than half degree. Then the obtuse angle of the prism is about 179 degrees. This is a biprism. These are the acute angles of about 0.5 degree. Then these two equal to 0.5 plus 0.5 1 degree. This is the obtuse angle. We know that the sum of the angles of a triangle is equal to 180 degrees. As these two angles are equal to 1 degree, the remaining angle is 179 degrees. This is a biprism which is used by Fresnel. Therefore, actually Fresnel's biprism is a single prism of obtuse angle 179 degrees. The action of the biprism is to produce coherent images of a given slit which are separated by a certain distance, and these two images act as two coherent sources. We know that in case of interference, two coherent sources must be present, but we cannot produce the phenomenon of coherence using two individual sources. Therefore, a single source is taken and it is divided into two wavefronts or two amplitudes. Then these two wavefronts are derived from the same wavefront and they satisfy the condition of coherence and interference fringes are formed. This is the biprism, and S is the narrow monochromatic source of light, vertical slit. The light from the slit is allowed to incident on this biprism. Biprism is placed with its refracting edge parallel to the slit S. As this is 179 degrees, it is just like a plain glass plate. Then these refracting edges are parallel to the vertical slit and the ray SB is perpendicular to the base AC. As this is a two-dimensional figure, we cannot see the three-dimensional image in this figure, but actually the slit S is vertical slit S is perpendicular to, the rays from the slit are perpendicular to the base of the prism. When light from S falls on the, these are the two refracting surfaces. This is a lower surface, this is a upper refracting surface. When the light from S falls on the lower portion of the prism, biprism, it is after refraction it bends upwards. After refraction it bends upwards. Then these rays, these refracted rays by the lower surface of the prism, when if you observe these refracted rays from this side, they appear to come from the source S2. Actually there is no source S2, but these rays, refracted rays, appear to come from the source S2. Similarly, the rays which are incident on the upper portion of the prism, they at this surface, refracting surface, after refraction they appear to the bent downwards, and these downward refracting rays appear to come from the virtual source S1. If you observe these rays from this side, they appear to come from two sources S1 and S2 instead of S. But actually S is the only single source, but refracting rays appear to come from two sources S1 and virtual sources S1 and S2. These two virtual sources S1 and S2 act as two coherent sources. Actually a single wavefront is divided into two wavefronts, that is one is refracting upwards, the second one toward downwards. These two wavefronts interfere with each other, and interference fringes are observed in the region EF. This is the wavefront moving upwards and this is the wavefront moving downwards. In this region these two wavefronts overlap each other, then they interfere with each other, and if you place a screen at this position, then interference fringes are observed, and in the region EF we can observe interference fringes. These fringes are observed through the eyepiece of the microscope. Next, using this experiment we can determine the wavelength of monochromatic light used. In general, in laboratories we use sodium light as monochromatic light of wavelength 5893 angstroms. This Fresnels biprism experiment is used to determine the wavelength of light of monochromatic source of light. In the theory of interference fringes, we have defined fringe width beta. Fringe width is nothing but it is the fringe width or bandwidth is defined as it is the distance between any two consecutive bright or dark bands, and it is denoted by beta. In this figure, the distance between two coherent virtual coherent images is denoted by 2 small d, and the distance between the source and the screen, this is the screen placed in front of the biprism, the distance between the source, that is slit, and the screen is capital D. D is the distance between the source and the screen. 2D is the distance between two virtual coherent sources S1 and S2. As refracting angles are small, S1 and S2 are very close to each other, are very close to, distance between S1 and S2 is very small. That is a definition of fringe width, and 2D is the distance between two virtual coherent sources, capital D is the distance between sources and the screen. Then the formula for wavelength of light in the theory of interference fringes, lambda is equal to beta into 2D by capital D. That is the formula for wavelength. For the determination of wavelength, the experimental setup is as shown in the figure. This is an optical bench, this is the slit from which light is allowed, and this is the biprism, and this is the microscope, and this lens is used for determination of 2D. All these four are arranged on the optical bench at the same height, and the heights and positions are adjusted to obtain interference fringes. The position of the source, the distance between the biprism and the slit and the microscope, all are adjusted to the same height, and they are adjusted to produce interference fringes, and they are observed through the eyepiece. First of all, the eyepiece is focused on its crosswires, and the vertical crosswire is made to coincide with one of the bright fringes. Then the reading is noted. First of all, the vertical crosswire is made to coincide with the one of the bright fringes in the interference pattern formed by biprism. Next, the eyepiece is moved across the fringes. The number of fringes that passes the crosswire are counted. By counting the number of fringes, again the vertical crosswire is made to coincide with another bright fringe. Again the reading of the micrometer is noted. Difference of these two readings is equal to distance moved by the screw. We know that fringe width is equal to distance moved by the screw by number of fringes. We have already calculated distance moved by the screw by calculating the difference between the two readings, and the number of rings are counted by viewing the fringes through micrometer. Then fringe width is calculated. In this way, the mean distance between two consecutive bright fringes is found, which is nothing but fringe width. This is the procedure for the determination of fringe width in biprism experiment. Once again, the eyepiece is focused to crosswires. First of all, the vertical crosswire is made to coincide one of the fringes, and the reading of the micrometer is noted. The eyepiece is moved across the fringes by counting the fringes. Again it is made to coincide with another fringe. Then again reading is noted. The difference of these two readings gives distance moved by the screw. We have already counted the number of fringes that passes the crosswire. Then we know that fringe width is equal to distance moved by number of fringes. By calculating this value, we can get the fringe width. In the formula for lambda, there are three factors. The first one is fringe width. We have already discussed. The second one is distance between the source and the screen. The third one is distance between two virtual coherent sources. We have already discussed about this fringe width. Then the second one is capital D, measurement of capital D. Distance between the slit and the eyepiece can be read directly on the optical bench. On the optical bench there is a scale on the optical bench. Here there is some scale. Then the distance between the source and the micrometer. Here this is a screen. Therefore the distance between 1 and 4 is directly measured by the scale on the optical bench. Next, the important point measurement is 2D, which is distance between two virtual coherent sources. As they are virtual sources, we cannot capture the image directly on the screen. For this purpose, we use another method, that is a convex lens of focal length 1/4 of the distance between the eyepiece and biprism. This is the biprism, this is the screen or eyepiece. This is the distance between the biprism and the screen. For example, if it is 80 centimeters, then 1/4 is 20 centimeters. Then a lens having focal length less than 20 centimeters, that is a lens having 1/4 less than 1/4 of the distance between the eyepiece and the biprism is taken, and it is placed between a biprism and the micrometer. Biprism and the micrometer. This is the lens placed in between biprism and the micrometer. To determine D, a lens of focal length less than 1/4 of the distance between eyepiece and biprism is placed between eyepiece and biprism. This is the lens placed at this position. This is the distance between two virtual coherent sources 2D. In this case, S1 and S2 are the objects for this lens. 2D is the distance between these two. This is the length of the object. For example, this is the length of the object. S1, S2 is equal to 2D. Then at one position, the magnified images of the slits are observed on the screen. This is the object for the lens. This is the lens. Therefore, this is object distance U and this is the image distance V. We know that these are the images formed on the screen. D1 is the distance between the two images. The lens is, in the first case, the object distance is U, image distance is V, the size of the image is D1 and size of the object is 2D. We know that magnification is equal to distance of the image by distance of the object or size of the image by size of the object. In this case, D1 by 2D, size of the image by size of the object, is equal to distance of the image by distance of the object. Now the lens is adjusted to another position, then we get a sharp images, small images are observed, diminished images are observed. Then the distance between, this is the second position. This case is observed when U and V are interchanged. Then the object distance becomes image distance becomes object distance. In first case, object distance is U, image distance is V. In the second position, object distance becomes V and the image distance becomes U. Then you get diminished images. This distance is D2. This is the size of the image. This is the size of the object. In both the positions, the size of the object is same, but size of the images are different. In first case it is D1, in the second case it is D2. In the second case, for the same formula for magnification, size of the image is D2, size of the object is same, and the U and V are interchanged. Then the formula for magnification in the second position of the lens is this much. So multiplying equations 1 and 2, you get 2D is equal to root of D1 D2. D1 and D2 are measured by the micrometer in just like fringe width, and object and image distance are measured by the scale on the micrometer. Then distance between two virtual sources is measured by measuring D1 and D2. This is another method for the measurement of 2D. This is called as deviation method. By substituting the values of capital D, small d and beta, we can determine the wavelength of monochromatic source of light. That is about measurement of wavelength using Fresnels, wavelength of sodium light using Fresnels biprism. Assignment. What is a biprism? How wavelength of monochromatic light is used using biprism? This question is generally asked in university examinations, and This is the assignment for you. I conclude this topic once again. A biprism is used to show the phenomenon of interference. First of all, this biprism is used by Fresnel, therefore it is called as Fresnel's biprism. Fresnel's biprism is a combination of two acute angle prisms, but it is a single prism having 179 degrees. The action of the biprism is to produce two coherent sources by the division of wavefront, and when they superimpose each other, interference fringes are observed on the screen. That is the main functioning of the biprism. Then lambda wavelength of light is determined using this experiment. That is about Fresnel's biprism and determination of wavelength.